In the field of science, the huge mysteries pertaining to what was prior to the enormous explosion have sparked mixed conversations and fascinated thinkers for quite some time. This enormous question tests more than just our ability to decode the universe, it challenges the actual boundaries of human knowledge. Imagine yourself at the brink of existence, examining the colossus shadowing everything and pondering what lay there. What existed before our universe was imagined? The Big Bang established the beginning of time, space, and all that we know. But in any case, were you there a moment earlier? Could there have been a state of nothingness? A calm before the cosmic gathering began? If this is accurate, then maybe there was something much more alarming that existed before the beginning of time. As we continue with this inquiry, science takes us on a journey beyond the universe's beginning point, into thoughts that challenge our consciousness. Physicist Brian Cox, well known for his examination of the marvel of the universe, suggests that something surprising might have existed before the massive explosion. He directs us to reconsider our thoughts of reality and existence. In this investigation, we dissect theories, research, and dazzling insider secrets that might explain what existed prior to everything. We will explore ideas like self-importance, inflation, quantum alterations, dark energy, and multiverse as well. The answers provided may just overwhelm you, yet they could also unlock new understandings of our place in the universe. Get ready to plunge headlong into a world beyond imagination and science, where the unknown still weaves through the shadows, shocking scientists and sometimes even making them angry. We ought to investigate what existed prior to the Big Bang. These theories cast doubt on everything we thought we knew. To appreciate what may have existed before the Big Bang, we first need to painstakingly examine what the Big Bang truly was. The Big Bang, as scientists define it, refers to the moment when the universe became extremely hot and dense, rapidly expanding to kickstart the development of all matter, energy, and innumerable forces. We can see evidence of this rapid expansion in the night sky, galaxies spreading out in different directions from an early starting point. But why did this happen? Furthermore, was there a period before this dense, hot beginning? As suggested by the theory of cosmic inflation, there was a before. It wasn't even close to void or tranquil. Instead, the theory suggests the universe was in a cold, empty, and unorganized state, much like an enormous vacuum. But this vacuum wasn't entirely empty. It contained an enormous amount of energy that powered the rapid expansion of space itself. This expansion, called inflation, happened so rapidly that it established the groundwork for everything to come. Space increased at unimaginable rates until the expansion slowed, and the energy transformed into matter, atoms and the forces we recognize as the Big Bang. But what was this energy used for? Why did it suddenly cause the universe to grow, and why did it stop? Experts think that this incredible expansion caused each patch of the universe to undergo its own Big Bang. Think of a fabric stretching indefinitely, with minuscule air pockets forming, each pocket representing a universe, including our own. This idea, called the inflationary multiverse, suggests there could be limitless Big Bangs and infinite universes. The one we live in is just one of many. This enormous, perplexing reality challenges our understanding of the universe itself and leads us to inquire about alternatives. Is nothingness before the Big Bang purely speculative, not real? According to our current understanding, even if you remove energy, particles, and radiation from the universe, it still wouldn't be a genuine void. Our universe is filled with dark matter, dark energy, quantum fields, and other factors that create a rich tapestry, even in its most empty-seeming state. Even if we imagine removing everything, the universe would still generate new energy. This alone is bewildering. It suggests that true nothingness might be impossible in our infinite universe. Space itself has properties, rules and constants, that prevent it from being totally empty. Imagine constructing a region with no particles, radiation, or energy, except quantum fields and fundamental constants. These would continue to exist. This implies that non-existence has properties. For instance, there's a phenomenon known as zero-point energy. It represents the lowest possible energy condition of quantum fields. Even in this state, particles can temporarily appear and vanish, creating a subtle resonance of movement, even in what should be a void. This challenges our idea of a real void and suggests that, indeed, prior to the Big Bang, there was a phenomenon only now beginning to be understood. One astounding theory in current cosmology is the idea of timeless expansion. Our universe, influenced by inflation, may continue forever. Brian Cox describes astonishing levels of inflation in the multiverse, the location of infinitely created and expanding universes. Each Big Bang could be a flash lighting another universe, while different regions continue to experience inflation, producing countless other universes. This cycle could, in theory, go on for eternity. This idea gives birth to the concept of a fractal universe, where each universe can produce its own Big Bang. Each universe exists independently and is not affected by others due to the rapid expansion of space. This hypothesis is both exhilarating and harrowing, as it suggests a multiverse without end, a structure with no beginning or conclusion. What if the upsetting fact is that there is no before or after, but rather a continuous pattern of universe formation and decay? According to quantum field theory, the universe is more than just a collection of matter. It's a complex network of energy fields that fill the universe and connect everything. These fields are like invisible oceans. Waves or particles act as disturbances. Even in their lowest energy state, the vacuum state, particles can briefly appear and vanish. This results in virtual particles, substances that exist momentarily and leave behind a trace of their presence. This casts doubt on the notion of true emptiness. Even in an empty universe, fields would remain active, sometimes creating transient particles. The constant, subtle movement in the absence of anything suggests the universe doesn't recognize our concept of emptiness. Fields and forces continue to fill space with hidden energy, making absolute nothingness impossible. This leads to an intriguing question: could fields produce particles and matter? Could the universe have emerged from a void filled with quantum fields? Dark energy is a mysterious force currently driving the accelerated expansion of the universe. But did dark energy exist before the Big Bang? Some theories say yes. They suggest that the dark energy we observe today is a remnant of an energy field that existed before our universe's formation. The properties of dark energy point to a hidden force that may have controlled the inflationary stage, causing rapid expansion. If dark energy existed before the Big Bang, could it have shaped the conditions that led to the universe's birth? Could dark energy be the silent architect of inflation, or even the actual beginning of our universe? If true, dark energy might hold the key to unlocking the secrets of the multiverse itself. Another intriguing concept: gravitational waves. These ripples in space and time, brought about by massive cosmic events, such as colliding black holes or the violent moments following the Big Bang, carry information about conditions that existed in the earliest instance of our universe. Scientists believe that if we can detect the faint echoes of gravitational waves from before or during inflation, we might gain direct evidence of what happened before the Big Bang. These signals could hold the signature of a pre-Big Bang event or even another universe colliding with ours, offering a potential window into a reality that predates known time. The quest to understand these waves has led to the development of advanced detectors like LIGO and the upcoming LISA mission, both designed to capture these almost imperceptible tremors in the cosmic fabric. If such evidence is found, it could fundamentally change our understanding of existence, pointing to a reality far older, and perhaps far stranger, than anything we've imagined. So, what truly existed before the Big Bang? Was it a vast, cold vacuum pregnant with energy? A churning sea of quantum fields? A prior universe that collapsed and was reborn? Or was it a timeless, ever-inflating multiverse, endlessly spawning realities? Each theory bends our perceptions of time, matter, and cause and effect. They challenge the deeply human need for a clear beginning and end, forcing us to think beyond linearity and into cycles, probabilities, and infinite possibilities. Ultimately, the question of what existed before the Big Bang may never have a final answer. But in asking, in exploring, and in continuing the search, we inch closer to understanding not only our universe, but ourselves. Because perhaps the real mystery isn't just what came before the universe, but why we are here at all to ask that question. Scientists believe cosmic events, if early-stage waves are ever found, could reveal new understandings of the universe's earliest times. These waves might serve as echoes of what came before the Big Bang. If they can be identified, they could provide evidence of the universe's previous existence. The possibility of discovering gravitational waves in their early stages is one of the most intriguing prospects in contemporary cosmology. It may not only expose the truth regarding the Big Bang but also provide a glimpse of the cosmic state prior to the birth of our universe. This theory presents a tempting possibility: detecting waves of gravitation that could act as traces of an earlier Big Bang universe. As we continue to investigate what could have been present before the Big Bang, we explore ideas that push the limits of our comprehension, challenging even our most fundamental assumptions regarding space, time, and existence. One of the most mind-boggling ideas comes from the realm of quantum gravity, which aims to meld general relativity with quantum mechanics. This merger could potentially expose a single theory of everything and provide insight into what existed before the Big Bang. According to quantum gravity, time and space are not smooth, continuous entities as we experience them, but instead are hidden, granular structures. This theory suggests that the space-time fabric itself could have been formed from a microscopic Planck-scale structure, with tiny quantum fluctuations shaping the universe in ways we cannot yet fully comprehend. What we perceive as the smooth space-time continuum may have only emerged from these ever-changing quantum fields. This perspective implies that time might have emerged only after a certain point, with the Big Bang potentially describable by an entirely different idea of reality, one where space and time lacked completeness. Another possibility is that the universe is part of a vast cosmic landscape filled with potential universes, each with different physical laws and constants. This theory, based on string theory, holds that all fundamental particles are, in fact, extremely small strings that vibrate within various configurations. Each of these configurations represents a distinct set of physical laws. The string landscape implies that our universe may be only one of many, each emerging from its own distinct Big Bang, if such a thing exists. This landscape also introduces the notion that other universes might have different dimensions, different strengths of gravity, or even different types of matter. From this perspective, our universe's matter may not be unique, but part of a collection of universes called the multiverse, each independently developing. The multiverse theory offers a hypothetical yet intriguing response to the question of what came before the Big Bang, another universe, arranged in a different way, potentially leading to infinite cycles of development and collapse, without a definitive origin. In addition to these ideas, some theoretical models of the cosmos have considered the role of black holes in shaping the nature of the universe. One hypothesis suggests that our universe may be the result of the formation of a black hole in another universe. In this scenario, the singularity at the center of a black hole could serve as a gateway to another cosmos. This hypothesis posits that the Big Bang was the moment when a similar black hole produced our universe. According to general relativity, the singularity at a black hole's center is a point where space and time curve infinitely, creating a region where the known laws of physics may fail. The extreme conditions inside black holes might result in the birth of new universes, suggesting that the Big Bang was merely the emergence of one from the collapse of a long-dead black hole. Exploring these concepts requires a deep examination of the very nature of time itself. Some cosmologists speculate that time, as we recognize it, might not have meant anything before the Big Bang. If time began with the Big Bang, then there may have been no before in any standard sense. According to this view, time may have emerged from a quantum fluctuation or a primordial state where the usual distinctions between past, present, and future did not exist. This could force us to rethink the concept of causality, which depends on the idea that events occur in a straight line. If time did not exist as we experience it, then asking what preceded the Big Bang may be absurd, as there would be no temporal framework to support such a notion. Further complicating the picture are theories of cyclic time. In the past, cyclic cosmology has suggested that the universe goes through innumerable cycles of birth, development, and collapse. In this model, the Big Bang may symbolize only the most recent bounce in an infinite series of cosmic cycles. These cycles might not be identical, changing in different ways and directions, each with unique physical properties. Based on this theory, the universe's cycle would be a continual process with no true beginning or end, rendering the question of before the Big Bang meaningless. According to this view, the notion of the Big Bang itself could be cyclical, with each Big Bang followed by a contraction and another cosmic crunch, restarting the universe in an endless loop. Another avenue of analysis involves the character and possibilities of a primordial soup of particles and fields that existed before stars and galaxies formed. This concept suggests that before the universe began its rapid expansion, it was filled with a dense and hot mixture of elementary particles, quarks, leptons, and bosons, existing in a state of extreme energy. These particles would have interacted at extremely high densities and temperatures, laying the groundwork for the formation of energy and matter. Some versions of this theory suggest that this soup existed in a realm where quantum foam particles constantly emerged and vanished, due to the uncertainty principle of quantum mechanics. The properties of this quantum soup could potentially provide an understanding of the universe's earliest moments, and by extension, what ultimately preceded the Big Bang. The world before the Big Bang remains one of the greatest mysteries in science. As our understanding of quantum mechanics, cosmology, and fundamental physics deepens, new theories will continue to emerge, offering increasingly complex, and sometimes paradoxical, explanations for the origins of our universe. While we may never fully grasp what existed prior to the Big Bang, the pursuit of this knowledge continues to push the boundaries of human curiosity, motivating us to investigate the unknown, the very edges of existence. As we push deeper into the frontier of pre-Big Bang speculation, we encounter ideas that challenge not only our physical theories but also our philosophical understanding of existence. The search for a theory that unifies the quantum and the cosmic continues to be one of the most ambitious quests in all of science. One compelling idea gaining traction is that our universe could be a hologram, an illusion of three-dimensional space projected from information encoded on a two-dimensional surface. In this holographic principle, space and time may not be fundamental constructs but emergent phenomena, born from deeper layers of quantum information. This view radically reshapes the question of before the Big Bang. If space and time are emergent, then their origin isn't tied to a singular moment like the Big Bang, but instead arises gradually from a timeless, information-rich domain. In such a framework, the boundaries of the universe may not be physical, but conceptual, limits in our understanding of how information becomes reality. Other models, such as loop quantum cosmology, suggest that the Big Bang was not a beginning but a bounce from a previous contracting universe. According to this theory, as the universe shrinks under gravity, quantum effects take over at extreme densities, preventing total collapse and causing a rebound, ushering in a new expansion phase. This cosmological bounce introduces the notion of a universe without origin, oscillating forever through cycles of collapse and rebirth. In such a universe, each Big Bang is both an end and a beginning, blurring the distinction between before and after. Adding further depth, some physicists propose the existence of a timeless quantum state from which the universe tunnels into existence, a phenomenon akin to spontaneous appearance without a cause, governed by quantum mechanics. This doesn't require a cause or a pre-existing space. Rather, it posits that the universe's birth was a quantum leap from nothingness to something. Here, nothing is not the absence of all, but a seething void of quantum potential, where fluctuations can momentarily give rise to existence. This quantum genesis is mysterious, yet it aligns with principles observed in particle physics, where particles can pop in and out of existence. If this is true, then the Big Bang was not an explosion in space but the emergence of space itself. Time, under this framework, did not begin at a fixed point, it evolved from quantum timelessness into classical flow. Such visions of the cosmos, cyclical, emergent, bouncing, or born from quantum nothingness, each offer glimpses into an invisible domain of reality that lies just beyond our observational reach. They reveal a universe that is far more nuanced, dynamic, and strange than we ever imagined. And perhaps, that is the greatest takeaway, not necessarily to find a single, definite answer to what came before the Big Bang, but to recognize the vastness of possibilities and the power of imagination and inquiry in the face of the unknown. For in seeking the origin of time, we may ultimately come closer to understanding ourselves, beings of stardust, curiosity, and relentless wonder, staring into the void and daring to ask the impossible.